Okay, welcome to the class. We have been discussing this DMRS. We'll finish discussing this DMRS generation. Okay, and I promise that we'll discuss it in finish discussing it in the last class. We could not finish this. We'll finish it now, and then we'll start discussing this sounding reference signal generation, how they are generated in the standard. Okay, so this is what we saw. I'll quickly run through this. So first, this reference symbol, QPSK modulated reference symbols are designed, okay, and later on they are multiplied with this orthogonal code cover sequences. And this slide and the next slide is telling us how these orthogonal code cover sequences are applied onto these reference symbols, QPSK modulated reference symbols. Okay, so I showed you this formula, okay, and basically this is the amplification factor. These are the orthogonal covers, okay, which are used to finally generate the orthogonal cover, which is used to create that orthogonal covering, okay, right, and it is a generic formula which is used for both type 1 and type 2, okay, and so this is L dash is 0 for single symbol, 0 1 for double symbol. These sequences are given in table below, okay. We saw that if you look at directly at this, it doesn't make sense, but if you substitute these values over here, it will be clear what is happening, okay, and that's what I am going to show you immediately, okay. So, but one thing is clear, that this table is meant for type 1, okay, wherein like you see the maximum 8 ports can be defined, okay, right, and there are these different groups, but how many groups are there? Okay, only 2 groups, CDM group 0 and CDM group 1. Okay, so if you have to go to type 2, there should be 3 different CDM groups. Okay, correct, and so this is limited to the type 1. Okay, this formula is applicable for both type 1 and type 2. This WF and WT which are coming over here. See, F is frequency, other one is time. Okay. So, we will see that how this is used, okay. I take up this example, okay, wherein this, what is this? This is double symbol, okay, and what is this? This is type 1 double symbol, okay. How many CDM groups are there? Group 0 and group 1, okay, 2 different groups. That is what is shown in the last table, okay, right. So, you see that this is much better seen now, okay, and so what is happening over here? So, let us look at this A, K, L, okay, and this is the port, okay. So, what is coming over here? If you substitute everything over here, okay, so it will be clear what is happening, okay. So, if you look at this, let us try to basically see what is happening. L dash is 0 for single symbol, 0 and 1 for double symbol, okay. What is L bar? L bar is basically the starting of the DMRS, okay. So, this what will this index tell, okay, whether you are in the first symbol, this is the starting, okay, whether you are in the first symbol or in the second symbol. L dash is 0, it means that you are looking at this symbol. L dash is 1, what is that? You are looking at this symbol. What is this? K dash and 0 and 1, you are looking at these subcarriers, right, okay, correct, that is what is happening, okay, and what this is some running index, okay, correct. So, if you have to, so basically what are we saying here? We have to generate this orthogonal code cover, okay, for the CDM group 0, okay, that is what it is, okay, when the port 0 0 0, okay. Now, if you look at this, you substitute K dash 0, okay, and L dash 0, what are you going to get? Okay, multiply. So, what is happening? You are multiplying WF K dash 0 and WF L dash 0. Okay, which position is going to generate? Is going to generate this position, right? Okay, so what is happening? K dash 0 and L dash 0, product of them is positive, right? That is what is coming over here. Okay, then you increment, if you can increment, so if you want to go to the time domain, what will you have to increment? You will have to increment L dash, because L dash will be 1 for the second symbol. That is what I said in the last slide. Okay, correct. So, if you make L dash as 1, what will happen over here? You are moving over here. Okay, so what is this? L dash is 1, you multiply it with K dash is equal to 0, because this is the first subcarrier, correct. Okay, so what am I saying here? To generate this particular value which is positive, okay, how will you generate it? You have to look at this, okay. What are you doing here? What is this formula telling you? This is the amplification factor, Okay. What is this? K dash is 0, n is 0, that is the running index. Okay. What will happen? It will be r of 0. You take the first symbol, okay, correct, and what are you doing? Then you will multiply it with the product of these two, correct, okay, and the product of these two for this position, what is it coming? It is positive. So you take this symbol and multiply it with a positive value. That is the first bit of that 4-bit orthogonal code cover. Okay, right. Now you want to see this, what is this value? What will you do? You will increment L dash, you will keep K dash as same, okay, because you are still looking at the first subcarrier, right. Okay, so what is happening? You see this K dash is 0, L dash is 1, you again get positive, that is what is coming over here, right. Okay, so you take so you have incremented K dash to 1, you get the first, n is still 0, right. So what will happen? You will have the first, this was 0, okay, so you will get the first value that of the DMRS multiplied with +1, that is what you did for the first time, you did this, okay. For the second one also, for the second symbol, what you will do? You will have to multiply it with +1 because that is the sequence, this multiplied with this, right, okay. Look at this now, okay. What happens? K dash, you will have to move to the first one because you are incrementing along the frequency, right. What will happen? K dash is 1, you look at L dash is 0, it is again positive, multiply this, okay, right. You take the third, so what will happen over here? You will move on to 0, 1, you will move on to the second one, okay. Second value, this 0, 1, and basically the third value, the index by second, it will get multiplied by +1 again, that is what is happening. Fourth one will also, you will get this +1 and +1. So that is why that is how this 4-bit orthogonal code cover is created, right. So 0 gets multiplied, r of 0 gets multiplied by plus, r of 1 also gets multiplied by plus, r of 2 gets multiplied by plus, and r of 3 will get multiplied by, okay. Now you move, if this is the port, what happens? For this port, you see this plus minus, okay. So K dash 0 and L dash 0 will give you +1 and +1, that is what is coming over here, right, okay. And here K dash 0 and L dash 1 again +1 and +1, so that is what is coming over here, plus, right. Is it clear what am I saying here? Okay. If you move along time for this port, correct. So this, how will you move along time in this table? You take K dash is equal to 0, you move from L dash, so this is the first bit which is this, what will be the second bit? You move along time, okay, from L dash is equal to 0 to L dash is equal to 1, what is happening? +1, it again gets multiplied by +1, right. So this is the second, fine, okay. What happens to the third one? Which is coming over the second subcarrier, okay. What happens? K dash becomes -1, you multiply -1 with +1, this is -1, you multiply, and then you have to move along time, okay. So you will move from here to here, you will, earlier you were multiplying K dash is equal to 1 with L dash is equal to 0, you got -1, and then you move from L dash is equal to 0 to L dash is equal to 1 to check for this, it's again minus, right, okay. So that is how it is created, okay, that is how it is defined in the standard, and this is the formula, okay, right. So you look at this, so how this will actually tell you, okay, that if K dash is for this type, for type 1 configuration, look at this, delta is basically come over here, okay, delta is 0, okay, you will have to move on by K dash is equal to 0, so you will hop from one to other, that is what it is telling you. Okay, you are looking at this, see, for configuration type 1 you are hopping every even times, okay, right, that is the expression which is coming over here, okay. So that is how you generate, I have given you like broadly how it is generated, okay, right. So this is how the orthogonal code cover is generated, okay. So this is, we took an example for type 1 double symbol, okay. Similar table should be there for type 2 also, okay, right. So this brings us to the end of basically this DMRS generation. Similar, you can take an example for type 2 also and can do that as an homework exercise, okay. So it is, the logic is same, okay, fine. So this is how DMRS are defined in the standard. From here on, we will move on to this SRS generation, Okay. So similarly, see the SRS also needs to be generated for different number of ports, okay, right, and you will see that they need to be generated for different users also. Okay. So we will see that how that is done. Okay. So what are we doing here? Okay. Basically, before we get into the details of understanding SRS, it's good to recapture why SRS is even required. Okay. Forget MIMO, it is like even if basically user has a single antenna, okay, right, then and the base station has to precode the PDSCH, okay, it should know this channel, okay, it should know the downlink channel, okay, correct. And how does it estimate this downlink channel? The use case which we have been considering is basically the TDD based beamforming, correct. Okay. So what happens? So these are the two problems which GNV faces before it can precode PDSCH. Okay. GNV needs to estimate the channel and know the MCS. Okay. We have seen this. Okay. No point in spending too much of time over here. So what we are saying here is GNV operates in TDD mode, okay, where it can easily infer downlink channel from uplink channel. This is an assumption, okay, right. We have discussed this in detail. Okay. So what is this concept of SRS? Okay, for estimating the uplink channel, UE transmits the pilot X to the G node B. Okay. Pilot is called the sounding reference signal. Okay. And how does that happen? This is, we are calling this as pilot. Okay. So you see this the single antenna, right? How many layers can be transmitted? What is the rank of this channel? Rank of the channel will be 1. Okay. Correct. Okay. And now how many ports you need for this user? You need only a single SRS port, right? Okay. And so that's what is being transmitted. This is a simple example, okay, wherein we are doing it over a single subcarrier, correct. And this subcarrier, this pilot is transmitted and it's received here, okay, over 2 antennas. And I'm not even talking about multiple SRS ports. This is only single SRS port, okay, correct. And so this SRS is transmitted. Then you get, for our first antenna, you get y1 is equal to h1x plus n1. These are two system of the equations. Okay, so y1 is h1 plus n1, y2 is h2 plus n2. Correct. Okay, it gets multiplied by x. And what have we done here? When from here to here. So this is the actual received signal over 2 antennas. While writing from here to here, I have set x as 1. Okay, just for the sake of simplicity. Okay, so these are the channel estimates. But this is an SRS, okay, right. So in this case, we are only talking about a single port SRS, okay, and I am going to discuss in this class how this different SRS are defined. That's all, okay. And this is one of the examples where we have used the SRS, okay. So there are other examples wherein like SRS are used, okay. Now this is basically the example which we have been discussing in this case, in our class. So downlink channel acquisition, assuming TDD reciprocity. There are other uses of SRS, okay, which we have not discussed. Initial scheduling, okay, right. So the user enters the network, right, okay, and so base station does not know its channel, okay. It's a 100 megahertz wide channel, right? And each user will have a different channel. Now base station has to estimate, has to find out how is this particular user channel who has just entered the network, how does it come to know, how does it estimate. So basically assigns this SRS to the user sends this SRS to the base station, and base station is able to find out how this like 100 megahertz channel or a part of 100 megahertz channel looks like for this user, okay, correct. And that's a very important concept, okay, that see there is a 100 megahertz channel, okay, and there are different kind of users in the system, okay. Let's say there is a IoT user, okay, a massive machine type communication user, which is operating in a very narrow bandwidth part, right, okay. As we discussed earlier, like 5G is designed for different kind of users, right. And then some of these users, they have very tight energy requirements, like a water meter, okay. It will not be operating in 100 megahertz, it will be operating in very small bandwidth part. So for this user, the base station would like to find out a channel in very narrow bandwidth part when compared with a like high bandwidth user, okay. So the idea is that base station has to find out the channel of each and every user before it can schedule this user, right? Okay, so that's what I'm saying here. This SRS is used for initial scheduling also. Okay, forget this downlink channel acquisition, it comes later. Okay, even before I have to do simple scheduling, I have to have this initial estimate of the channel. Okay, right? And then the final use is basically the way we use, you remember CSIRS for the downlink to calculate the MCS information, right? Okay, so if this TDD reciprocity is applicable in the downlink, it is applicable in the uplink as well. Okay, right? So what happens here? So UE estimates the downlink channel using CSIRS, okay, right? And since the channel is reciprocal, okay, it knows the uplink channel under reciprocity assumption. Now UE designs the precoder for the uplink, not the base station, okay, and it precodes this SRS, and then base station using this precoded SRS, okay, calculates the uplink MCS and then reports it back to the user so that it can use that particular MCS for the uplink. You get that? Okay, what are we saying here? This is exactly opposite of what we did for the downlink. Okay, in the downlink, what happened? Okay, base station used the precoded CSIRS. Here it is using the UE is using the precoded SRS. Okay, for the base station to find out the equivalent MCS for the uplink. Right? Okay, so that's another use case which we never touched upon. There was not a need, but this is also done. Okay, so these are three broad use cases of SRS. Okay, right? And now I'll show you how it is defined in the standard. Okay, fine. Look at this. Okay, so SRS, first thing is, okay, unlike DMRS, okay, it is limited to a maximum of 4 antenna ports. Okay, right? And there is a reason, okay, why this is limited to 4 antenna ports, why this in the downlink there are maximum of 12 DMRS ports. Okay, UE is basically limited by the uplink is limited by the UE power. Okay, and so typically UE power is on a lower side than the base station power. Okay, right? So you cannot, it is difficult to support more than 4 layers in the uplink. That's what people have realized, okay, with all the uplink constraints. Okay, let me put it this way. Okay, with all the downlink constraint, people have done their simulations and research to figure out that maximum 12 layers can be supported in the downlink, but in the uplink only 4 layers can be supported. Okay, so you see this, there is a difference in the way SRS is designed. Okay, only 4 antenna ports. Okay, right? And so what is this? This is the time symbol duration. Okay, this is N SRS, and the symbol is the number of symbols over which the SRS is defined. Okay, right? So SRS time duration can be 1 symbol. You look at this, correct? Or 2 or 4 consecutive symbols within a slot. So here it is 4 consecutive symbols. Now always consecutive symbols. Okay, and you will see here, so the starting symbol location is denoted as L0, something similar to what we saw for DMRS also. Okay, and starting symbol, you see this here where it is coming towards the end. Okay, so what is this telling? What is this bullet telling us? That the starting symbol can be located anywhere within the last 6 OFDM symbols, okay, of a slot, provided the resource does not cross the end of the slot boundary. What is it saying? That this SRS has to lie within this slot. Okay, that's how typically we always transmit. Okay, but what is this? This is so fine. So these are some aspects. Okay, what are we saying here? That SRS is defined only for a maximum of 4 antenna ports, okay, and they typically come at the end of the slot. Okay, why? First, if you see that what happens in the first part of the slot is typically allocated for the downlink, right? Okay, this is the first two symbols is PDCCS transmission, next few symbols will be PDSCS transmission. Okay, if it is basically the TDD system, then you switch only towards the end of a slot, correct? Okay, so that part is only the uplink transmission. That's why you see this SRS coming only at the end. Okay, here it is coming at the last 4 symbols, here it is coming in the second last symbol. But you look at this bullet, what is it saying? It can come anywhere within the last 6 OFDM symbols. You cannot say that, okay, it will come in this last 6 symbols, because it will cross the slot boundary. Okay, so you have to follow that basic rule, okay, that SRS should not cross the slot boundary. Okay. Now, so what is this? You should get used to this terminology. SRS has actually a COM structure. What is this COM? You look at this. Okay, then here it is easier to see. Okay, these are the brushes of the COM. Okay, right, and that's why it is called a COM structure. Okay, typically coming at the end. Okay, this end, if you see, it looks like a COM. Okay, it's not coming somewhere in the middle. Okay, and so COM spacing is either 2 symbol. Okay, they are separated by basically this. So KTC has a COM spacing. Okay, is either 2 or 4, not symbols. Okay, is either 2 or 4. Okay, and what are we saying? Is either separated by 2 resource element, or is either separated by 4 resource elements. That's what this bullet is telling. Okay, fine. And then this is a symbol which is used in the standard to decide whether this COM spacing is 2 or 4, KTC. Okay, then what does this technically mean? Okay, what does this COM spacing mean? It means that SRS is transmitted on every nth subcarrier where n can be 2 or 4. If COM spacing is 2, the SRS will be transmitted on this every second subcarrier. Okay, and if the COM spacing is 4, it will be transmitted on every 4th subcarrier. Fine. Okay, so what is this COM spacing allowing us to do? SRS structure allows frequency domain multiplexing of different SRS of different UEs. Okay, right. So what is happening over here? So why it is designed like this? Okay, as I said, for each UE, base station has to find out the channel. Let's say it is initial scheduling. Okay, a user is entering the network. Okay, and the base station has to sound out. Okay, that's the term which is technically used. Base station has to sound out the channel of each user. Okay, basically figure out how good or bad this a particular bandwidth part of each user is. Okay, so it will assign, let's say, this comp, okay, for this particular user, for a particular user. Okay, right, and in the standard, so if it has to like find out the channel of second user, it will assign the second comp. Okay, right. So I have shown it for one PRB. Okay, this is will extend it for, let's say, 275 PRBs. Okay, this comp can be defined over 275 PRBs. Okay, so by using this kind of a comp, a base station will be able to find out the channel of the entire channel of UE1, and then what it will do, it will know the channel over these subcarriers. Over this it will interpolate. Correct. Okay. And similarly for the second user, it will assign the other comp, which will be offset by this one symbol. Correct. Okay, right, and so it will be able to find out basically the complete, let's say, 100 megahertz channel, just for an example. Okay, right, and for different users. Okay, now this is how many users can be multiplexed with this kind of comp structure? Only 2. Right, how many can be how many UEs can be simultaneously sounded out with this COM2 over one symbol? Only 2, right? One will be assigned for this, for UE1, and then offset it will be assigned to the UE2. Correct? Okay. Is this clear? What am I saying here? That COM2 structure in this case can allow you to multiplex only 2 users. Okay. That's why different COM structure is defined. Okay. So different COMs are offset by each other by integer number of REs. Okay, so here they are offset by 1, here they are offset by 4, right? Okay, so what's happening here? If this is, now look at this COM structure. Okay, what happens here? That this COM structure is basically, let's say it is for one user. Okay, correct. Then for the second user, I can offset as by 1. Okay, right, and I can assign it to the second user. Similarly, I can do for another 2 users, right. So, this kind of COM structure is allowing me to multiplex 4 different users, and base station can find out the entire frequency domain channel of all these 4 users, right, simultaneously. I have to like sound out 4 users, I will do this allocation, okay, correct. If I have to sound out 2 users, I will do this allocation, okay. And this, if you look at this, why this is done, basically this also we are going to discuss in detail, okay. You see this, there are like 4 adjacent symbols, okay. Why is this being done? Let us say UE is in a poor SNR condition, correct, okay, and the channel does not change much, okay. So, this is because the channel remains constant, then the channel can be basically averaged to improve the SNR, right, okay. So, that is why one reason wherein like you see this kind of COM structure. So, all 4 contiguous, it can be 2 also, okay, or it can be 4 depending on how bad or good the UE channel condition or SNR conditions are, okay, but it allows to basically sound out 4 different users. And so, this is something called the COM offset kappa bar TC, which is defined with respect to a PRB boundary, okay. So, this I will cover these aspects when we talk about this frequency hopping, okay. So, there is this COM offset which is defined, okay, with respect to a PRB boundary, okay, and where is this COM coming, okay, that is what it typically tells that, okay. And there is a repetition factor also associated. Once we start talking about the frequency hopping, that is how this is done. These 2 aspects I mentioned, okay, just for the record, their use will become clear when we start talking about this frequency hopping structure. Okay, I will take an example, okay, to basically tell you that how this COM structures are used for different users, okay, right. So, look at this. So, this is physical, so COM spacing and offset example. So, that was the example I was giving you, okay, right. So, this is the COM offset, this is one COM for being used for user blue, this is another COM being used for user green, right, okay, correct. That is what we said, okay, that for this kind of COM you can multiplex 2 different users, right, okay. So, that is what is happening, okay. Now, so and here this COM spacing is how much? COM spacing is 2, right, okay, and here you look at it, how much is the COM spacing? COM spacing is 4, right, okay. And what are we saying here? SRS with a COM spacing of 4 has a lesser density than COM spacing of 2, okay. So, this what kind of, how many like SRS you can design, how many users you can multiplex with this kind of COM spacing? Look at this, okay. Here every alternate RE is being used as SRS, here every 4th RE is being used as SRS, okay, but there is no repetition along time, okay, right. So, we have taken this COM structure, okay, further reduced it, okay, to allow standard allows that, okay. So, what is happening here? These 2 users, okay, so this COM is allowed for user 1, here this COM is allowed for user 2, right. This is another user, user 3, a separate COM is defined, okay. Here, so every 4th RE is used as a SRS, okay. This is user yellow, for that again a separate COM is defined, okay. So, for this kind of COM, how many users I can multiplex? I can multiplex 4 different users. I have shown only 2 over here, okay, but I can multiplex 2 more users and sound out their channel also as well, okay. How have I been able to achieve this? Basically reducing the number of REs which have used for defining the SRS, okay, SRS COM. Here every alternate is being used, RE is being used, here every 4th RE is being used for one COM, okay. So, this is COM 1, this is second COM, COM 3rd and COM 4th are not being used, okay. I can use that also, okay, right. So, standard gives this kind of flexibility in designing the COM, which will help in basically sounding out the channel of different users simultaneously, okay, right, because what is happening here, by allocating one COM to user 1 and another COM to user 2, all these I am able, as a base station I am able to figure out or the estimate channel of these 2 users in the same symbol itself, right, an entire let us say 275 PRB channel which is 100 megahertz channel, okay. So, this is one, Here also same thing is possible, but with the lower density, right. So, here you will get better interpolation, here you will get the poorer interpolation. It depends on what kind of user this is. If it is a, let us say, IoT user which does not require this kind of good channel estimates, okay, where the data rate is low, this kind of pilot assignment could, SRS assignment could be done. If it is basically high data rate user where the channel estimates have to be extremely good, right, you will have to do this kind of assignment, or application based, okay, if it is a voice application, right, it is okay if the estimates are poor, okay, that receiver quality, receive signal quality can be slightly poorer than wherein it is a URLC user, okay, wherein you cannot afford to have a poor quality channel estimate because the reliability is important, latency is important, okay. So, it is a function of all that, okay. So, the standard gives us this kind of flexibility. We will continue discussing this in the next class also. Thank you.